אני אלמד אותך באמת לא אומרים את האדום, לא? כל שבוע אני אתרגל אותך פה עד שתדע לעשות את זה. בואי להגיד שאת בחורה.
אני לא יודעת.
רואים את האדום גם.
זה הכי חנוני לעשות את זה בכיתה הבאה.
לא נורא, זה מה יש. לא נורא, זה יש כאן רק חנונים.
רואה, זה מציל.
כל אחד שיעמוד ליד האות שהכי גורמת לו. גליה לא באה להגדי. אני גם לא אהיה ביום.
לא נורא, עזבו, בוא נעשה וזהו. יאללה, בוא נעשה. וואי,
אבל אני רוצה שתואר
אני מתעניין שלא קשור ולא מעניין גדי. הוא טען שהוא לא קשור. מי זה?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
אני לא יודעת שמות של אנשים. אני לא אכפת מה.
טוב, תוסיפו את קמיני וכל החבר'ה בפוטושופ.
זה לא כולם. בואי נעשה נקבע מתי את רוצה שאני אעשה. אני לא הולכת לעשות על הטלפון.
אני מוכן לשלוח את זה ליד מאוחר. למה הוא הדליק פה את
הוא לא עשה עם זה טוב, יאללה, זה מושלם. כן, אבל רואים שאנשים גבוהים לא יפתירו.
רואים מאחורה.
רואים בצד. רואים פה. אני מוכן לעשות לך בסדר. לא, תראה, את הפייס. עוד קצת. לך ימינה, תשווה את הפייס. לא, תקח שב על זה. אני אעבור לא לאף אחד בית.
I can't be like one of your friends,
אני
girl.
בטוח לא מסתירה כלום.
רק רגע.
לא, עכשיו אני מוסתרת.
רואים את התמר?
רגע, רואים את תמר? רואים את האורץ? רגע, רואים נראה לי שפה זה.
בסדר, מוכנים? כולם מוכנים?
רואים הכתוב? אוקיי. עכשיו אפשר לתת. מתפקים לצחוק. מטריד? אפשר למחוק את זה טוב? זה סלאמה. אני למחוק את זה. אנחנו צילמנו דיונים. אנחנו מספקים להם 2,
האמת שגם עשיתי קורס אחר
3, 4. כאילו זו התמונה הכי טובה. חושבי שזה לא מצגת. נראה לי תככבי שם.
אין זאת.
לא היו בוחנים את תהליכים.
איזה 2? עם הבן שלך. 2. לא, זאת בעצם.
Okay, hi everyone. Sorry for being late. Last time we were talking about limit cycles, and I told you that there are a few methods to rule out a limit cycle, and even less methods to prove that there is a limit cycle. So today we're going to go over these. Ruling out the limit cycles. We're going to see two methods. And then let's call it establishing no. You can call it proving a limit cycle. This is the Poincare Bendixson theorem. We'll get to that, I think, in the next hour. Okay, so gradient systems. Okay, we have this general system. Given. And for some systems, we may be able to find some function, some scalar function, v of the x vector, gives you a scalar quantity for every combination of x and y, for every coordinate, such that our time derivative of x is minus the gradient of v, and v is a continuously differentiable single-valued scalar function. Continuously differentiable So if we can find this v that is continuously differentiable, single-valued and scalar, such that our x vector dot is minus the gradient of v, and I'll give the definition of the gradient in a moment. So if we found this, then the system f of x vector is called the gradient system. And then v is called its potential function. Okay, and now the gradient of v is just taking the partial derivative of v, and each partial derivative multiplies the direction along which it is calculated. Sorry, this should be a circumflex over x1 and x2. The circumflex means a normalized vector in the direction x1. So, okay, so x1 kind of be something like this. Or, I don't remember if this should be written like this, but anyway, it's just a direction, the normal direction vector. Like 0, 1, and 1, 0 in the Cartesian coordinates. So in our case, x1 is just x, and x2 is just y. And this is our gradient. What this function v say what it means is that if a system is a gradient system, we can describe the dynamics of the system as a flow according to some field, okay, to some potential. For each point on the phase plane, there is some potential. You can imagine it as an electrical potential. And our system is a point. It could be, for example, like a charge that is attracted to, let's say, a positive charge that is attracted to the negative potentials and repelled from the positive ones. Or a different analogy would be a topographic surface. So in a gradient system, we are able to describe this system as a topographic surface, and then our point will be like a ball rolling down the hills into the valleys. And apparently not all dynamical systems can be described this way. Some dynamical systems do other stranger things. So we can say that V is a surface where minima are the stable fixed points and maxima the unstable fixed points. Now, we have a theorem that tells us that closed orbits are impossible in a gradient system. Yes? It's kind of how you define your potential. So you could define your surface as a surface where the maxima are the stable fixed point and everything is attracted upwards. It's just a convention. That things go down the surface. Setting up a computer to show a demonstration later on. Okay, I'm going to show a short proof of this theorem, and later on something more intuitive. Okay. Okay, so say there is a closed orbit in the system. Closed orbit C. Okay? Then delta V for a trajectory from T until some delta T, or, sorry, some T plus capital T, should be 0, okay? say we have a gradient system and there is a closed orbit. So our system is doing this trail along the surface, okay? And it's finishing the trail in the same height where it started. Okay? So we can write this. So we can actually write this delta V as an integral over the time derivative of V from 0 to capital T. And then by the chain rule, we break V down into its components, okay? So for the first component, we'll have dV to dx1. And by the chain rule, we need to have also dx1 over dt, which is the first component of this, okay? So by the chain rule, we can write this as the gradient of V times x dot vector. And then we have the dt still outside.
Why can you substitute delta V for in the first step for dv dt times dt?
This?
Yeah.
So I
No, not this.
here?
Why you
Because I kind of break the time into small increments, and I say that if this is continuously differentiable, so it has okay, so we didn't say it's over time, but I'm saying the integral is just the delta.
why isn't it just dv dt?
Integral over of dv over dt. No, you can't have that. You must. But the integral is over time, so
Okay, yeah.
we're looking for the change. Okay. So we open this, and by the definition of V, this is just minus x vector dot. Okay, so this is like saying so no square. And then we got something squared here that must be 0. Okay. So we got that x vector dot must equal 0, or the 0 vector. But this means that there was no change in y or x over time. I mean, or actually this means that this system must be at its fixed point, okay? But we said this is a closed orbit. Okay, so we contradicted our initial assumption, and this means that it is impossible to have a closed orbit. Let's turn on the projector. Oh, it's on? Okay, and on a side note, I want to say that most 2D systems are actually not gradient systems. So in a minority of cases, probably you will be able to rule out a limit cycle using by finding that the system is a gradient system. So this is one tool that applies to some of the 2D linear systems, or some of the 2D systems in general. but all 1D systems are gradient systems. And again, we see that the limit cycle or the oscillations are things that cannot happen in the 1D system. Okay. Is it? Oh, it's not connected yet. Okay, so the idea that I want to show here is why intuitively there cannot be limit cycles in a gradient system. And say we have a gradient system, okay? So it might have a surface, okay, with an unstable fixed point, and where we would think there might be a limit cycle, but you can immediately see that a ball that you would put here would have no reason to keep revolving around this valley, around the sombrero. And for that, you will need to have the Escher stairs, which is, of course, impossible. Okay, so if we have a gradient system, we cannot keep revolving according to some potential function. And I just want to mention that the Escher stairs were actually conceived by Roger Penrose, who is a mathematician and physicist that you may have heard of. So he actually thought of this structure and wrote Escher about it, and then Escher drew it. And he thought about it. When he thought about it, he was actually inspired by Escher's works. I'm going to do an example of how we check whether a system is a gradient system. Okay, you told me last time that it's hard to see this way, right? It's too hard. And if I write on the board like this, what? Okay. I'm just trying. I will want to show another thing on the MATLAB, and I don't want to turn off the projector. Okay, so the easy way to find out whether a system is a gradient system is to use the fact that in a gradient system, we have df over dy equal to dg over dx, okay? So you have a symmetric Jacobian, even before you substitute any fixed point into it, okay? So when you are given some system, then you can immediately check if the Jacobian of the system is symmetric. Say again? If it's symmetric for some gradient? Yeah. Yeah. So you can immediately say this system is a gradient system. There are no limit cycles. Okay. Sometimes you want or you will be asked to find V. Okay. Or you will be asked to skip this step and just show this according to whether or not you can find this potential function. So what we are doing is partial integration of both functions. Okay, right. So x dot equals. And I'm going to show this with an example. Okay, so just note that here we can easily find that the Jacobian is symmetric. So this will be 6x, right? And this will be minus 4x equal to y. So this is symmetric, and the system is a gradient system. When we do the partial integration, we take each equation at a time and we integrate it according to its variable. Okay? So I write that I'm integrating the first equation to find some tentative v that I mark with a tilde, which is the integration according to x of 3x squared minus 1 minus e to the 2y. Okay, so this would be minus x to the third plus x plus x e to the 2y. And of course, there may be some function that is only a function of y, or either a constant, that can come out in the integration and it's kind of invisible when you take the derivative with respect to x. Okay, so you must always allow the option of something that was dependent only on y, and then it did not show in the derivative according to x. And this is why this is tentative, okay, because I don't know whether this exists or what it is. And I do the same for the y equation. So I'll call this v bar. Yes.
Why are you looking for v?
I want to know this potential function. I don't need it because I have that, but yeah. But sometimes I want to find v. Okay. Okay, so you can already see that I can kind of combine these two. Okay. In order to find the actual v. Let's do this here. I can also say that by the definition of v, it's not here, where minus the gradient of v equals the x vector dot. I know that if I take dv over dx, it should be equal to minus x dot. Okay, So, and now, for example, let's take this one, the tentative v that I got from the integration with respect to y, and I take this dv bar over dx. So I have this plus the derivative of this k function that I don't know. And this should be equal to the 3x squared minus 1 minus e to the 2. Okay. Oh, no. Okay, this is not here. Okay, so this cancels out, and what we have here is that dk over dx equals 3x squared minus 1. And what I'm trying to show here is that these are the only things that I need. This x e to the 2y, and the kx is actually these two, minus x to the third plus x. So I write that v equals minus x to the third plus x e to the 2y. So there is a v. I was able to find a potential function, and therefore there can be no limit cycle. Another way to this one, it's actually okay. So from here I found that dk over dx is 3x squared minus 1. So I can integrate it and find what k should be. So it's a kind of more formal way than just looking at this and looking at this and seeing what the final expression, the actual v should be. So here I see that there might be something that depends only on y. Here I see that it doesn't come out. Okay, and here I see that there should be something that depends only on x, and here I see that there are these two expressions. And this is here I kind of find that they are. But you can just go intuitively and combine these and compose your v. Yeah. No, if you know that J is symmetric, you know that there is no limit cycle. Sorry. Okay, this means J is symmetric. So.
Does it mean that it's J symmetric?
Okay.
If all I want to do is prove that there is no limit cycle, it's enough to show that J is symmetric, or should you have?
It's enough to show that J is symmetric unless you are told explicitly to find V. Okay? Because I do want to see that you can find this V. Another way to see that there can be no limit cycle, okay, and this is maybe more obvious, is that this system does not have fixed points. So.
Enough just to show the one partial derivative? Enough?
Say again?
You just found one partial derivative.
Where?
dE.
This one? Yeah, I can do also d of v wave for the
And
y.
one is enough, right?
Well, it should be enough, yeah.
Okay.
This even is a bit redundant. What? Say again?
What's going on in the left line?
I found a v, so there exists a v, so there is no limit cycle.
Finding a v means that
Yeah.
you found what?
That this is a gradient system. There are two ways to show that this is a gradient system.
Okay.
One is to show that J is symmetric,
Okay.
and the other is to find a potential function.
Okay.
It's actually equivalent, because what we had here with this one and this one, it kind of relates to to this thing. But you don't need to see the connection. Only I'm telling you, you have this condition, and alternatively, you can try to find the potential function. And another way is, for this system specifically, there are no fixed points, okay?
No, but I still don't understand the logic behind this, because you
This?
use the first line as a condition, and I
This
don't.
thing?
This we said is the condition, right?
Yeah, this is the
must
condition.
be true if this is.
Okay, so now I'm checking if my v bar.
Mhm.
So my v bar is an expression where I don't know everything,
Yeah.
right? So I'm checking what should happen. What should I do so that this v bar is the complete v?
Okay.
Okay? So I'm saying if it is the complete v, then if I differentiate it with respect to x, then I should get 3x squared minus 1 minus e to the 2y.
Okay.
And then I get a condition on this. So I can know what is this k. Okay? I did not know it. Now I know it.
Will this not be possible if I get dk dx equals dk dx plus 1? Or when will this not be?
When will this not be possible?
Yeah.
If
Seems like you can
okay,
always
if for some reason there is something here that is wait. If you have other terms, for example, if for some reason you have some other function of y here that does not appear here, okay, if you so it's a good way to check yourself. Okay. This should you should be able to do this. You should be able to fulfill this condition. Okay.
But then you need to be able to match it to the V2 so that you calculate it.
To what?
To the
To this one.
yeah.
Yeah. Yeah. It's kind of closing the circle and seeing that you're okay. Okay.
Can you give an example maybe for a J that is not symmetric?
And then you cannot find a V?
Then you cannot find a V?
Let's see. Well,
What would be the dead end in which
so here, okay, I changed the system. I added a plus y here. Okay, so this means that here I have plus y, and here I will have minus xy. Okay, and then I don't have this term here. Okay, and it cannot be inside k of x. Okay, so you see that there is something that does not match. Is the projector on? Okay, I'm going to show. I'm going to take 5 minutes and show this example I have on MATLAB. The projector will turn on. Oh. Okay. Okay. This is our system. Okay. We had y dot equals minus 2x e to the 2y. Which gives us an oak line here, this red line. Okay. Y dot equals minus. Okay, so y dot equals 0. You have x equals 0 as your null line. It's red. And we also had x dot equals 3x squared minus 1 minus e to the 2y. And if you take that to be 0, you get e to the 2y equals 3x squared minus 1. And then you have y equals 1/2 logarithm of 3x squared minus 1. Okay, and this is the logarithm. Okay, and it exists here too because the x is square. So these are the null lines, the green and the red. And I hope you can see in the shades of gray, where you have black here and white here and shades here, this is v that we found, this potential function. And in this demonstration, I show how things run away from the white area and into the black area. Okay, and of course, according to the null line. So the black is this kind of valley that everything falls down into. Okay, and white is this mountain that just roll off from. Okay, and this is what we have with the gradient system. I think I had another one that was nice. Okay, so this is a more complex situation for x dot equals y plus 2xy, y dot equals x plus x squared minus y, and then the v is minus xy minus x squared y plus y squared over 2. And here, I wanted to show this because this is a gradient system that has fixed points, in contrast to the previous one. Here and here we have fixed points. And you can see this gradient, this potential function has this mountain here and here, and another one here, and valleys here. And we see how the system is rolling off the mountain into the valleys. And also, we can try to see what happens around the fixed points. Okay. So if you imagine this as two mountains and in between there is a saddle, okay, you see things that can roll from the mountains into the saddle and then they roll to either of the sides. Okay? And this shows you why this type of fixed point is called a saddle. Now I'll check the other fixed point now. Oh, another fixed point that I did not mention here. This is a stable fixed point. It's kind of it would be a pool between the mountains. Okay, so I hope you can all picture this as this landscape where we have in between the three mountains we have this place that is high, but inside it there is a basin of attraction. So when you roll off the mountain, you can either go over there and flow, say, to the river or to the sea, or roll to this pool here, which is the stable fixed point. Okay, so we take a 10-minute break, and then we continue with the Lyapunov function.
זה צריך, אבל גם בלי מילים, פשוט תמונות.
מעניין, אבל זה לא הקשבת לי. עכשיו היינו תקלים. מה הבעיה?
כן, תתחיל, צריך. לא, אני לא אצלם, זה לא המומחיות שלי. לא, הזווית, הפרופורציה. לא, כי אני כבר מופיע... יואב אמר, תלך להיות שלט? יש לנו דרך לעשות את זה, אפשר להגיד שהיא הוריסטית, ואז אני רוצה הצגה תוספתית. לא באמת אז בדרך כלל הוריסטית היא להשוות אותם. ולהגיד, XY, פה לא קיבלתי שום דבר אז פה יש לי באמת שני דברים, X ו-Y, ואז מה שאנחנו זה ביטוי. רגע, התשובה, אבל תעשה איזה ביטוי לא תביא ואז אם נגזור את זה לא, נגזור את זה הקומבינציה
What is the local minimum that those are the stable fixed points, okay? And the maximum are the
עכשיו מצטלם. בוא בוצע. כן, כן.
יש לי שאלה משהו.
אם יש את האינטגרל x, אז עכשיו היא גוזרת לפי y? איך אני גוזרת? יש לך z dy, התוצאה היא לא שזה שווה. אם אני עושה את זה, אז יוצא לי פה 2x ו2 יצא לי משהו אחר, אז הייתי פשוט צריך, רגע, אני צריך לסגור ולהשוות לזה, ואז אני יכול לבודד את זה.
סבבה. אבל מה? זה אני מבין, אבל איך יכול להיות מה לפי? מה זה?
כאילו יש נקודות שבאמת נגיד ידעים כן, מינוס.
Now it seems like sort of back to normal.
הנה, ראיתי עוד פעם בחוץ. מה זה? condition. זה אתה שם ל-initial condition כאילו?
נראה לי שאתה, יש לך משהו כזה, כאילו אתה point.
כן, זה initial condition. ואז איך עושים? האינטגרציה נראית כמו שאנחנו עושים בתרגיל?
כן,
אוילר כמו שלנו? זה שואל זה למטה פה כאילו...
אוקיי.
פעם זה נחמד, במקום כל פעם להריץ את זה.
כזה דבר, H זה האקסיס, אתה פותח את יכול לעשות H שווה אקסיס פשוט, אז להתחיל לצייר. וגם בפלוט אתה יכול לכתוב H ואז כאילו HY. הנקודה הראשונה
פשוט האקסיס זה מילה שמורה?
אקסיס זה מילה שמורה, כן. זה פותח אקסיס, אתה יכול גם, יש פה גם סימן.
זה אחרי שאתה כותב פיגר, אני אומר.
כן. זה ההנדל של האקסיס, ואז כל פקודה מקבלת את ההנדל הזה, אימפוינט מההנדל הזה. זה לא, שאתה לא ממש חייב, אתה מקבל אובייקט שהוא כן, C, ואז אתה עושה get position.
לא שואל, זה נקרא כבר, זה לא מסובך.
כן.
האימפוינט
זה משהו. הבעיה היחידה שלי היא שאין לי דרך לסגור את זה, ואז
מה זה לסגור?
כשאני עושה, בגלל שאני רוצה לקחת נקודה, ואז להריץ את הסימולציה, ואני רוצה שזה ייקח לי עוד נקודה. ואז להריץ את הסימולציה. אני עושה פשוט while 1 ו...
while 1,
ואז כל פעם נותן לי לבחור עוד נקודה, ואז אין לי דרך יש, כשאתה נותן
אתה יכול לעשות משהו שהוא יקבל, אם תלחץ על איזה כפתור, אז ה-1 יהפוך כמו אינפוט כזה.
זה כבר לבנות את כשאתה עושה אינפוינט, זה מאוד שימושי נגיד כשאתה עושה אנליזה, אז אתה יכול לעשות אינפוינט ואז כאילו נגיד אתה בוחר ריינג' בתוך הדאטה שלך, יש לך היסטוגרמה ואז אתה בוחר את המקום הזה כדי לחלק אותו לשתי קבוצות. זה ממש טוב. ואז אתה יכול לתת לו מספר נקודות שהוא יקבל, חתיכה 2, 3, ונדמה לי שאתה עושה
פה יש רק אחד כאילו?
כן, פה יש רק אחד, ואז אתה עושה ספייס והוא יצא משם. ספייס, מספר נקודות מסוים, זה יצא משם.
תודה.
Okay, before we move on, I want to tell you that I've checked your exercise 2, and I will put them in the box later on today, after the class. And I'll try to send the soft copies, anyone who submitted by email, I'll try to send it in the evening, and if I don't send, you can remind me. Your exercise 3. Is
it possible to send by email?
Yes, we do not.
Yeah. Yeah, it's possible. As a single PDF file. Maximum 2, okay? Now, your exercise 3, when did I say it is due? Second? Thursday, this Thursday, okay. And when we come back from for the next semester, I think we have 3 more lessons, and maybe I'll be able to add a 4th one because we didn't do everything we were supposed to. We'll start the next semester with one lesson about bifurcations in 2 dimensions. I mean, new types of bifurcations that we did not see in the 1 dimension. And then chaos theory, which is actually nonlinear 3-dimensional systems, which have new phenomena that we cannot even get in the 2 dimensions. And that's chaos. Okay. And after that, we go to the stochastic processes. The next way to rule out a limit cycle is through a Lyapunov function. Lyapunov function. Okay, remember we had this definition of Lyapunov stable, non-Lyapunov stable. Now this is a Lyapunov function, and when we see the chaos theory, we'll get also a Lyapunov exponent. So Lyapunov did have a lot of contributions to this field. So the concept is quite similar to a gradient system. We are going to try to find some function, the Lyapunov function, that meets certain criteria, and if we can find it, then we cannot have limit cycles. So this is an energy-like function that decreases along trajectories. So meaning that if there is a Lyapunov function, then our system's dynamics are such that with time, the Lyapunov function only decreases, okay? We are kind of losing energy and going to the lowest energy state, okay?
Is it different than what we saw with the gradient, when you showed us with the non-infinite values?
I'll show why it's a bit different.
Is the gradient system a special case of the Lyapunov function?
Let me think. Yeah, I think the gradient system will be a special case. Okay, so if it exists, then closed orbits are forbidden. And note that in the gradient system and here too, I use the term closed orbits. Okay, we have ways to rule out closed orbits, which are also what we get around centers. We don't have a rule to say that there are no limit cycles, but there can be closed orbits. Okay, we don't have something that differentiates between these two. Maybe the Poincare Bendixson theorem does differentiate. I don't remember, but we'll see that later. And the reasoning is similar. Okay, if you can't keep losing energy if you're going around in a circle. This is also a kind of scalar function on the x and y coordinates. Okay, so the more formal definition, okay. Let's say we have a system with a fixed point x star if we can find a Lyapunov function which should be continuously differentiable, real valued scalar function v of the x vector such that we meet two conditions. The Lyapunov function is positive for any point outside a fixed point, and it is 0 at the fixed point, okay? Meaning it is positive definite, okay? So with the gradient function, you know, it could have been also negative or so on, but of course in the gradient function you could add a scalar to it without it showing in the gradient. So this could still be met by a gradient function. Second condition, v dot is negative for all points outside the fixed point. Then x star is globally asymptotically stable. And there are no closed orbits.
Is the first condition for all x equals to x star?
For all x different, okay, and at x star it is 0, okay. Okay, so there is no systematic way to find a Lyapunov function, but there are good guesses, okay. So a lot of times a sum of squares is a good guess.
Can you maybe just explain what those two things, what those conditions are, and what the function is?
Yeah. So we are looking for a function that is positive definite. It's always either 0 or positive. And specifically, at the fixed point, it is 0. And for any other place, it is positive. Okay?
So it's any function that will give us a positive value.
Yeah.
Okay.
It give you a positive value outside the fixed point, 0 at the fixed point, and its dot, its time derivative, is always negative outside of the fixed point. Inside the fixed point, obviously, it's 0. Okay? Yeah, okay, so like I said, there is no systematic way to construct this function, but usually we try sums of squares. So in this example, okay, we have this system. Now, if we calculate its Jacobian, we see that it is not symmetric. This is not a gradient system. And we can immediately see that 0, 0 is a fixed point, And if we put it here, we get a trace of -1 and a determinant of 4. So it is a stable node. Actually a spiral, right? Specifically, it's a spiral. So now we are trying sums of squares. And I just want to say that given a system, you can try to see if it's a gradient system. You can try to see if it's a Lyapunov function. Kind of use your methods in order to try and rule out limit cycles. Okay, so we'll guess a v that is x squared plus ay squared. And we don't know this a. We are saying there might be a function that looks like this. And for a specific a, it might meet those conditions. So we can take v dot, right? We just differentiate this with respect to time. So we get 2x x dot plus 2ay y dot. And then we can just substitute because we know x dot and y dot. So we get minus 2x squared plus 8y minus 2axy, 8xy, right? Minus 2ay to the fourth. Okay, and we're saying that the condition is, okay, the first condition was met because it's a sum of squares, right? Always positive except at 0, 0, which is our fixed point. Now, for the second condition to be met, then we need to have this negative or at the fixed point equal to 0. And then we can choose a that will be suitable, okay? So first of all, we see that this is negative except that x equals 0. If a is positive, then this is negative, okay? And we assume that a is positive, right? Because we want this v to be positive definite. So if a is positive, this is also negative. These two are negative. We don't need to care about them. And then we want these to cancel out, so everything will be negative. So we can choose a equals 4, and then this v dot is negative anywhere except in the fixed point in the origin of axes. So we have v dot equals minus 2x squared minus 8y to the fourth. And this is smaller than 0 for outside the fixed point and equals to 0 at the fixed point. Yeah. And then v equals x squared plus 4y squared, which is positive outside the fixed point, and it's equal to 0 at the fixed point. And so v is a Lyapunov function, is Lyapunov function, and there are no closed orbits. Now I wanted to show this in MATLAB, but I don't have time. I'll just say that if we have a spiral, then this is already a case that we cannot have with the gradient systems. Okay, so the we have a fixed point with trajectories spiraling into it, this is not something that we get with a gradient system. In a gradient system, things just go downhill. Okay. I want to cover the Poincare-Bendixson theorem before the end of the lesson. And there is a nice example from an applied model in which we will show this theorem. Okay, so the Poincare-Bendixson theorem in which we are proving that there exists a limit cycle somewhere in the system. Okay? Okay. Let there be R, a closed bounded subset of our plane. And some dynamical system, a continuously differentiable vector field on an open set containing R. So, for example, on the real numbers. Bigger? Okay. On an open set, yeah, it became smaller. On an open set containing R. So, to illustrate this, we have the plane, the two-dimensional plane in which our dynamical system is operating, and we have some closed bounded set of the plane. This will be R. Later I'll refine it. Also, we ask that R contains no fixed point. Okay? So even if we have some fixed point, P, okay, then we will say that R does not include it. It might be a donut around P. Okay? And then the fourth thing that we want there to be here, see a trajectory confined in R. Meaning it starts in R and stays there always. So if there is some trajectory that starts within this region, R, okay, this is a trajectory C that never goes out of this region, okay, then we can say that C is a closed orbit or it spirals toward a closed orbit. As time goes to infinity. And in any case, we can say that R contains a closed orbit. Again, not committing to whether it's isolated, meaning a limit cycle, or non-isolated, meaning like the closed orbit surrounding a center.
Is there no condition on the trajectory C?
the condition is that it's bounded inside R.
No condition on its length.
No.
If it's short enough, then it
Well,
won't.
no, this is always. This is the condition, okay? Okay, so we're saying that if we found some trajectory C, then it must be a closed orbit, or it spirals into some closed orbit. Now I'm going to show how to use this theorem. Conditions 1 to 3 are the easier, okay? So we have our system, and we might be able to draw this boundary, but this subset R. But the tricky one is number 4. And then what we are going to do is to construct R as what we call a trapping region. So we are trying to craft this shape that will trap all the trajectories that might lie on its boundaries. So the trapping region is this, we call it a closed connected set for which the vector field points inwards, okay, on all of its borders. So we know our dynamical system that we got. We can draw its vector field, and then we are looking for some region that will be such that arrows only go into it and never out of it, okay? And then if there are no FPs, no fixed points within R, which is also something that we should show, then the theorem ensures us a closed orbit in R. Okay, so we can construct a trapping region, but there might be a fixed point that draws all the trajectories into it. Okay, so we are also demanding that there will be no fixed points within the trapping region. It's much more clear when you see the example, so I'm going to move to that. This is a model that was published, I think, in 1968 by Selkov, a Russian scientist, I think. 1968, a model of glycolysis. And there are a lot of there's a long way in the paper. There's a long way that leads to a non-dimensional system, like many transformations of variables and so on. And the final system is this. So glycolysis is the process in which organisms break down sugar, and it turns out that some cells, for example, yeast, can maintain an oscillatory mode of this glycolysis, and then we have these variables representing X, the concentration of ADP, adenosine diphosphate, and y, the concentration of abbreviated F6P fructose 6-phosphate. So we have these two compounds whose concentrations oscillate, okay? And this model was proposed in order to understand how this happens. So this is, of course, this is already a non-dimensional concentration, okay? It's a concentration divided by relevant concentrations in the system and so on. Okay, so the first thing we can do when we get such a model is find its null lines. So for the first one, we can write it like this. Y equals x over a plus x squared. Let's make a plot with the null lines here. Okay, we already know this type of function, or I hope you know how to draw this. Okay, we look what happens for small x. So for small x, this behaves like x over a. Just linear, yeah. And for large x, this behaves like 1 over x. Okay, and there is some transitional region in the middle. Okay. Yeah. Okay, so this is x dot equals 0. Y dot equals 0. And then we have y equals b over a plus x squared. So when x equals 0, this is just b over a. Okay, that would be the intersection here. B over a. Okay, I don't like the way I drew this. Not very useful for later. Okay, and this function decays like 1 over x squared. So it decays faster than the first one. Okay, and now we can ask what happens. I'll do this in red. What happens when y is larger than this? Okay. So when y is larger than this, here, then x dot is positive. When it is smaller, then x dot is negative. Now we look at this function. Okay, what happens when y is larger than this curve? So from here we see that when y is large, y dot is negative. Okay, so when y is larger than this expression, meaning we are above the blue line, then y dot is negative. Above the green line. Above the green line, we have a negative y dot. below the green line we have a positive y dot.
Have we done anything yet that's different than what we've
No.
normally been doing with null lines and stuff?
No.
Okay.
Okay, so I fill in for the regions bounded by the null lines. You can immediately see that there might be a limit cycle here, but there might also be a spiral, of course. Okay, and now we are going to try and construct a trapping region. Okay? I'm out of colors. So, okay, but I'll do it in red anyway. Red lines. Okay, so if I take this axis here, it's below both null lines. This is what we have. All the trajectories should go diagonally and cross this axis in such a way. Now we will take this axis, the y-axis, and it behaves similar to this region. Okay, at least below the b over a point. Okay, so already I have two lines with trajectories going into them. Now I'm going to take some vertical line here. Okay, so this has this kind of diagonal and this has this kind of diagonal. Things go in, right? Here, this is more tricky, so I'll leave it like this. Okay, and I can also draw a horizontal line here into which the trajectories go. Okay, so, and this is a fixed point, of course. So I'm on my way to construct the trapping region, and now the question is, how do I close it here? Okay, so what I can say is that I can go on indefinitely with this horizontal line. Okay, I don't care. So I'm controlling the slope of this side of the trapping region. I can use whatever slope I want, and I want to have a slope that is less steep than this. Okay, so I want to have a slope. Okay, let's say that this is like this, and my slope is less steep. So things will go into my region. This is a complicated example. In your exercise, you have a much easier example. So what is this slope? Okay, we know this slope. We can write an expression for it. It's y dot over x dot. Okay, slope y dot over x dot, and I can say, okay, like I said, I can take this indefinitely. Okay, I can move this indefinitely to the right. Okay, this area here. So I can choose to be at a region where x is large and y is large. When x is large and y is large, okay, these terms fall off. Okay, this is a cubic term. This is linear. This is constant. These terms fall off. Okay, so y dot over x dot equals -1. Okay, so if I take the border of my trapping region far away over there, then the slope of this field is approximately -1. And then I will construct my region with a slope that is less steep than -1. Okay? Say again? Why less steep? Because I want the trajectories to go into my region. So the trajectories have a slope of -1. That's just 45 degrees, right? So I want the border of the trapping region to be less steep. Okay, and then they will go in. And the final thing is to circle, to take out this portion here. So if this is an unstable fixed point, things will go into my region. Okay? If unstable, I have a trapping region. Okay. Okay. We don't have much left. Try to do it in 5 minutes. Okay, and this is what I showed here. I'm erasing this. A trapping region where things only go into it, and there is no fixed point within it. So over there, we know there is only this fixed point. We constructed something with things going in on the outside. And here, if this is an unstable fixed point, we can approach it to be close enough to the fixed point so everything will go out of the fixed point and into our region. This is something you can always do with an unstable fixed point. Yes?
Why can't it be other unstable fixed point in the region of this?
You mean if there were, it will still be a region, a trapping region. Yeah, it's true. Okay. Yeah, but I would still take them out, maybe. Inside the fixed point itself, you never, no, you stay there. It's okay. So, okay. Yeah, I guess you can leave unstable fixed points in the region. But then I have to take this out because, no. When it's stable, I have to take it out. When it's unstable, I don't really have to take it out. Yeah. So the practice is to take it out. Okay, just mark circles around the fixed points and take them out. But like you said, it's not necessary. Okay, so what we found is that we can construct a trapping region. And if we construct a trapping region, we prove that there is a closed orbit, or in fact a limit cycle, but only if the fixed point is unstable. And then we move the problem to a condition on this fixed point, the condition that it is unstable. If it's unstable, we have a limit cycle. Okay? The way to do this is to write, of course, the Jacobian. Y, and substitute the fixed point, and you can find the fixed point analytically by the intersection of the knock lines, and then you can get some expression, and you write its delta. You find that delta is a plus b squared, and it's always positive. That's already good. Okay, we don't have a saddle. And then we are left with checking whether tau is indeed positive. And then there is some condition on tau. If you substitute and then you calculate tau, you find that tau is minus 1 over a plus b squared times b to the fourth plus b to the second to a minus 1 a plus 1. Yeah. trace, yeah. Yeah. Tau is a trace in our course. So this is a quadratic equation on B square. Okay, so you can actually find where this is positive and so tau is negative, right? So if it's a quadratic equation, you can say basically what we have is a parabola for tau against B square, right? Tau is minus something. With we have this, and in fact the leading terms are the B square terms. So this becomes actually a condition over B square and a condition over B, and what you find out from all this is that you have certain combinations of A and B that give you an unstable fixed point, and certain combinations of A and B that gives you a stable fixed point. So this is B, A, and you can draw this region where this is unstable. FP, and then you have a limit cycle, and here you have a stable FP. And this is a stability diagram, like you also did in your exercise. only here, the stability diagram contains something that you could not get in the one-dimensional system. And we'll see in the next semester, we'll see what bifurcation occurs here. On a final note, I'd like to say that the Poincare-Bendixson theorem it poses a limit for the dynamics of the two-dimensional systems. It tells you that if you have a trapping region and everything goes into it, then things go into a certain closed orbit. That might be a limit cycle. Okay, and this is only true for the two-dimensional systems. In three-dimensional systems, you might be able to construct some donuts. Okay, like our trapping region, only with some volume, where everything goes into the donut, but inside there is no single closed orbit, and things just go around and around. You can imagine that if here you have a limit cycle, in 3 dimensions you can always go over and under this limit cycle, and this is what is called a strange attractor. And we'll deal with that in the next semester. So actually the Poincare-Bendixson shows you why chaotic phenomena like this strange attractor cannot happen in the 2D system. And have a good exam period. זהו, זה יוצא מהאזור שלך. אם היא יציבה, אין מה לעשות. אני טעיתי.
אם יציבה,
אז לא, זה לא יעבוד.
אנחנו לא יכולים לקחת משהו מסביב, אבל אנחנו יכולים לקחת משהו כאילו...
כן, נכון.
לא משהו ש...
נכון.
ואם זה לא יציב, אנחנו מציבים את זה.
אם אנחנו לא יציב, אם זה לא יציב...
סתם בגלל שבהגדרה...
רק בגלל ההגדרה, כן. נכון. בהגדרה צריך... כן.
זה שני קריטריונים שונים, גם
זה מין...
פרוג'קטורית וגם שלא מפקסים. אתה הגדרת את זה.
כן, אני נתתי כאילו... דרך לנסיעה שקראת לי. המשפט לא יורד. אם שניתחת ב-623 של הרבה, אז כן. 3 זה no fixed point, זה 4 זה...
שאלות את המסלול המעגלים, הטראג'קטורי
שיש לו שם מסלול סגור, ואז אם אני מצרף את העובדה שהתקופה תהיה אפסולו, אז ברור שזה כאילו, זה הגיוני מאוד להביא את האנטימדיה, אבל האם יש דרך כאילו פורמלית להראות את זה, או שזאת הדרך פורמלית? לתאר את זה? והשאלה השנייה שלי היא לגבי השיפוע הזה עם השיפוע. אמרנו שהשיפוע הוא y דוד x דוד כשאני לוקח את x, כאילו כשה-x גדול, כשאני לוקח...
לא, הוא תמיד y דוד x דוד, אבל בשקט הגדולים שנגיע לביטוי שיותר חיינו לטפל בו, אנחנו
x גדול.
x גדול ו-y גדול. רק ילד שעבוד.
הבנתי. אוקיי, סבבה. ולמה זה חשוב שהשיפוע הזה יהיה פחות תלוי מהשיפוע הזה?
השיפוע של מכאן זה פחות תלוי מהשיפוע של הוקטור.
של אוקיי, עכשיו הבנתי. כי אחרת הוא יחליק עליו, כן, הוא לא יחליק עליו.
שהם יצאו ממנו.
כן.
זה שנייה של סט איפה שנמצאים, אז הם יראו. אני חושבת שזה בגן יש כזה. אבל לא בגן, איך קוראים לו בעברית? אני מכירה את השם וואלאבי בעברית. כתבתי וואלאבי בעברית בגוגל.
כן, בכוונה זה מודל